In December of 1978, a power plant in Lower Saxony switched on that stores electricity in a hole in the ground. It is still running today, 48 years later, at 290 megawatts. The storage is compressed air, held in two salt caverns, 600 meters beneath a German field. Now here is the part almost nobody knows about compressing air, and it changes everything about how you would build a small one. The energy is not really in the air. It is in the heat of squeezing it. Let that heat escape and you have thrown away most of what you put in, which is exactly what that German plant does and why it burns natural gas to buy the heat back. Burying the tank is the cheapest solution to that problem anybody has ever found. Let us dive in. There is an energy storage device in most garages, and its owner thinks of it as a tool. Take an air compressor apart in your head. There is a motor, there is a pump the motor drives, and there is a steel tank the pump fills. Now watch what happens when it runs. Electrical energy comes in through the cord. The motor turns it into mechanical work. The pump uses that work to force air into the tank, and the tank holds it there, at pressure, until somebody opens a valve. That is a battery, charged from the wall, discharged through a hose. Nobody calls it one, because the output arrives as torque and impact and airflow, rather than as volts. But every element is present. Energy in, energy stored, energy out later, on demand, at a time of your choosing. And the storage part works remarkably well. A sealed tank holds its pressure for weeks. There is no self-discharge worth measuring, no chemistry aging inside it, no cycle count. Come back in a month, and the pressure gauge reads what it read when you left. Now the part that annoys everybody who owns one. The compressor cycles constantly. You are halfway through a job and the motor kicks in, drawing a heavy surge every time it starts, because starting a motor under load always does. It is the loudest object most people own. In a small workshop, conversation stops when it runs. And the reason it cycles so often is the tank. A 20-gallon reservoir empties quickly under any serious tool, so the motor restarts, over and over, running a punishing duty cycle for the whole afternoon. Which points at something worth noticing. In that entire machine, the storage is the cheapest component, the simplest, the one with nothing to wear out and the one nobody thinks about at all. Air is free, it is everywhere, and squeezing it stores work. Nothing about that process consumes anything. No material is used up, no reaction takes place, and nothing inside the tank changes chemically. The same air can be compressed and released 10,000 times. And it is exactly the air it started as. So look at what a steel tank does not have. No cycle count, no capacity fade, no electrolyte to dry out, no plates to corrode, no cells to balance. Nothing that catches fire, nothing that vents, nothing that needs a management system watching it. It works in a freezing shed in January and a baking one in August. Leave it charged for a year and it is still charged. And the discharge is instantaneous. Open a valve and full pressure arrives immediately, with no ramp, no sag, and no internal resistance limiting how fast it can leave. Every factory floor on Earth runs on this for exactly that reason, which makes compressed air look, at first glance, like the ideal storage medium. Everything about how well it actually performs comes down to a single variable, and it is not pressure. Squeeze a gas and it gets hot. That heating is not a side effect of storing the energy, it is where the energy went. Put your hand on the discharge line of a running compressor, and you will find it uncomfortably hot. Some machines run that line at well over 100 degrees. The heat is not friction or waste. It is the work your motor just did, showing up as faster moving molecules inside a smaller space. Now consider what happens next. In every garage on Earth, you fill the tank. The tank is warm. You go and do something else for 2 hours, and the tank cools back down to room temperature. The heat has left. Into the walls, into the air, into the concrete floor, and it took a large share of your stored energy with it. Engineers have names for the two extremes of this. Adiabatic means the heat stays inside, no thermal energy escapes during compression, so the gas ends up hot and holds everything you put in. Isothermal means the heat leaves exactly as fast as it appears, so the gas stays at ambient temperature throughout. Real compressors sit between the two and then drift toward isothermal while the tank sits idle. The same physics runs backwards on the way out. Releasing compressed air cools it sharply because the gas expands and its molecules slow down. This is why an airline frosts up during heavy use, why a duster can leave your fingers numb, and why industrial systems fight ice at the point of use. That cooling is the gas taking back energy it needs in order to expand, and if it cannot get that energy from somewhere, expansion stalls. So, let us find out what a tank in a yard actually holds. For isothermal expansion, the energy available is pressure times volume times the natural logarithm of the pressure ratio. Take a 30-gallon tank, which is 0.114 cubic meters, filled to 10 bar, roughly 145 psi, a normal working pressure for a decent compressor. 10 bar is 1 million pascals. The natural log of 10 is 2.3. 1 million times 0.114 times 2.3 gives about 262,000 joules. Divide by 3.6 million to convert into the unit on your electricity bill, and that is 0.073 kilowatt hours, 73 watt hours, before a single loss. Run it through a real motor at real efficiency, and you are looking at something in the region of 2 phone charges. And notice the shape of that equation, because it governs everything you might try next. The energy scales directly with volume, so doubling the tank doubles the storage. It scales with the logarithm of pressure, so doubling the pressure adds far less than you would hope while doubling the engineering difficulty, the danger, and the cost of the vessel. Which means compressed air at household scale is not going to store your evening. In December of 1978, in Huntorf, Lower Saxony, a power plant switched on that stores electricity in a hole in the ground. It is still running today. The builder was BBC Brown Boveri, and the name they gave it tells you how they thought about it. The gas turbine air storage peaking plant. Remember that phrasing, because it turns out to be more honest than anything written about the technology since. The storage is 2 salt caverns, not tanks, not vessels caverns, dissolved out of a natural salt dome by pumping water down and drawing brine back up. Together, they hold about 310,000 cubic meters of volume, 600 meters beneath a German field, and they operate between 43 and 70 bars. Off-peak electricity runs the compressors for roughly 8 hours, filling the caverns. When the grid needs power, the air comes back up and drives turbines. The plant is rated at 290 megawatts for 2 hours, and it was upgraded to 320 inches, 2006. Now the operational record, which is genuinely impressive and rarely mentioned. Across the decade from 1998 to 2008, Huntorf maintained a starting reliability between 91 and 92% and a running reliability above 96% for both its generating and compression sections. It can start from cold in about 5 minutes in an emergency, 10 to 12 minutes normally. It also has black start capability, which means it can bring itself up from nothing with no grid behind it, the kind of capability you want after a regional blackout, and something very few plants of any type can do. 48 years of service in a technology most people have never heard of. Then there is the number that reveals the flaw, and it comes straight from the physics of the last section. The round-trip efficiency of Huntorf is about 42%. Follow the heat and you will see exactly where it goes. The plant compresses air, and that air comes out of the compressors hot. Before it enters the cavern, it is cooled to roughly 50 degrees, because that is approximately the temperature of the salt wall down there, and hot air would damage the formation. All of that compression heat is dumped into the environment. Gone. So the air waiting in the cavern is at 50 degrees and high pressure. Release it through a turbine and it expands. An expanding gas gets cold enough to ice up the machinery and stall the process. The solution Huntorf uses is to burn natural gas and reheat the air on the way out, which produces the figures that define this technology. For every kilowatt hour of electricity the plant delivers, it consumes about 0.8 kilowatt hours of electricity and 1.6 kilowatt hours of natural gas. More gas than electricity. The original name was accurate then. This is not really a battery. It is a gas turbine that arrives at work with its compression already paid for. 13 years later, Alabama built the only other commercial plant of its kind, and it went after exactly that loss. McIntosh came online in June of 1991, 110 megawatts, storing air in a salt cavern of about 538,000 cubic meters, 450 meters down, running between 45 and 76 bars. The headline difference is duration. Huntorf discharges for 2 hours. McIntosh runs for up to 26. But the interesting change is a single component. The engineers added a recuperator, a heat exchanger sitting in the turbine exhaust, capturing waste heat on its way out and using it to preheat the incoming air before combustion. That one addition cut fuel consumption by roughly a quarter. The numbers move accordingly. McIntosh uses about 0.69 kilowatt hours of electricity and 1.17 of gas per kilowatt hour delivered, for a round-trip efficiency near 54%. 12 points better than Huntorf, achieved by refusing to throw away one stream of heat, which points directly at where the field went next. The Frontier version is called adiabatic compressed air energy storage, and the concept is simple to state. Instead of dumping compression heat into the atmosphere, you capture it in a separate thermal store, a mass of rock or oil or molten salt, and hold it there. When you release the air, you run it back through that store on its way to the turbine. The air arrives hot without burning anything. No gas, no combustion, no fuel bill, and round-trip efficiencies that climb toward what pumped hydro achieves. The economics have followed. Modern adiabatic designs come in around $120 per kilowatt hour of capacity, and very large systems built on cheap reservoirs drop below 50. Because enlarging the reservoir is the cheap part of the system, compressed air becomes cheaper than lithium once you need more than about 8 hours of storage. There is a reason only 2 commercial plants existed for decades, and it is not the machinery, it is geology. Both of them sit on salt domes, and salt domes are where they are. So, an entire industry, across half a century, has organized itself around one question. What do you do with the heat? Every serious effort in this field is trying to solve the same thing, which is what to do with the heat. A buried tank solves it by accident. Consider what surrounds a vessel a meter underground. Soil, in every direction, effectively without limit. And soil at that depth sits at a stable temperature all year. It barely notices the seasons, let alone the afternoon. That is a thermal reservoir, an enormous one, already there, costing nothing. Compress air into a buried tank, and the heat has somewhere to go. It moves out through the steel into ground that does not warm up in any meaningful way, no matter how much you give it, because the mass on the receiving end is measured in tons. Then, when you draw the air back out, the process runs in reverse. Expanding air cools the vessel becomes colder than the soil around it, and heat flows back in. The ground gives it back, which pushes the whole cycle toward the isothermal case from earlier heat, leaving steadily on the way in, arriving steadily on the way out, with the tank never straying far from ground temperature in either direction. The practical result is the thing a builder actually notices. The icing that plagues air systems under sustained draw is dramatically reduced, because the soil is feeding heat into the expansion as fast as the expansion removes it. No gas burner, no recuperator, no thermal store to engineer. Now let me be precise about what that does and does not buy you, because this is not a loophole. Burying the tank does not beat the arithmetic from earlier. 73 watt-hours in a 30-gallon vessel at 10 bar is the isothermal figure. It is the ceiling, not the floor. What the ground does is move a real system closer to that ceiling instead of well below it. Better, not magical. And 73 watt-hours is still 73 watt-hours. So compressed air at household scale is not going to run your house, and any video telling you otherwise has not done the multiplication. What it does exceptionally well is something else entirely, and it has been hiding in plain sight since the first section. Compressed air does not need to become electricity. Every conversion in a storage system costs you. Air to turbine, to generator, to inverter, to socket, and each step takes its share. But a nail gun, an impact wrench, a sander, a die grinder, A blowgun, none of those want electricity. They want pressure, which is what you already have. Run a tool straight off the tank, and the conversion loss is zero, because there is no conversion. The most important choice in this build is which vessel goes in the ground, and it is a safety decision rather than a performance one. If you want the full build, the vessel options, the burial detail, and the plumbing schedule, we put together a complete walkthrough covering everything here and more. The link is in the description below. There are two legitimate routes, and I want to be specific about both. The first is a vessel actually rated and sold for burial. Buried propane tanks are a standard product, engineered for exactly this service, with corrosion protection designed in from the factory. That is a vessel somebody qualified has already thought about, and it comes with a rating that means something. The second is a buried pipe array. Rated high-pressure pipe, run in loops, holding the same total volume as a tank, but spread across enormous surface area. That geometry does two things for you. It exchanges heat with the soil far better than a single fat cylinder, which is the entire point of burying it. And if a length ever does fail, it fails as a much smaller event than a large vessel, letting go all at once. Now the route that kills people, stated once and clearly. An ordinary compressor tank of unknown history, buried in soil, is a vessel you can never inspect again. It will rust from the inside, where the condensate sits, in a place you cannot see, on a schedule nobody is tracking. That is not a shortcut. That is a bomb, with a delay fuse made of corrosion. Assembly is straightforward once the vessel decision is made. Bed it below the frost line on compacted sand, level and fully supported along its length. Bring the connection and a drain point up to an accessible riser at the surface, so the plumbing stays where you can reach it. Fit a pressure relief valve rated below the vessel's own limit. Add an isolation valve at the surface. Then run the supply line to wherever the air is actually used. Now, 5 rules. 1. A pressure vessel failure is an explosion, not a leak. Compressor tanks do burst, they do kill people, and the usual cause is internal rust in a tank that nobody ever drained. 2. Never bury anything you cannot inspect or that is not rated for burial. Corrosion is invisible, and the consequence is not a slow hiss. 3. Drain the condensate religiously. Every compression cycle deposits water inside that vessel, and that water is what rusts it from within. On a buried tank, this stops being maintenance and becomes the only thing protecting you. 4. Never exceed the rated pressure, and never modify a vessel. No welding, no drilling, no fittings the manufacturer did not intend. Any modification voids the rating, and that rating is the only thing standing between you and Rule 1. 5. Relief valve, always. Correctly sized, tested, and never plugged. A pressure switch that fails closed will run the compressor until something gives, and the relief valve decides whether that something is a valve or the tank. This stores watt-hours, and a great deal of its value is not electrical at all. Say the honest part first. It will not run your house. It will not compete with a battery on energy. And the equation from earlier does not bend for anybody volume and the logarithm of pressure, and nothing else. What a buried reservoir genuinely gives you is a compressor that runs less often and lives longer, air that stays near ground temperature going in and coming back out, and a tool that works the instant you pull the trigger with nothing converting anything on the way. Plus the property it shares with that plant in Germany. Nothing inside it degrades. Not this year, not in 20. Huntorf has been running since 1978, and it burns natural gas to buy back the heat it threw away at the compressor. The entire modern field is a search for somewhere to put that heat. Your yard has been holding it the whole time. If discovering the practical, unglamorous corners of engineering matters to you, subscribing and sharing is the simplest way to make sure this kind of knowledge keeps being found. We will be tracking all of it as it develops. Now, tell me about yours. What does your compressor actually run, and how often does it cycle while you work? I read every single comment.